Hi, hello there, dearest attendees. My name's Philip, and I was incapable of providing a correct email for the BSides registration, which makes me equipped to talk to you about technology, and I work for Microsoft.
Hey everyone, my name is Amir. I'm a senior engineer in Microsoft Defender for Endpoint. Unlike Philip, I do remember my email address, so I send the right one, and that's it basically.
Right. So let's for a moment suppose that you've had the privilege to run a piece of malware on someone's computer. Now, don't worry, this is the only meme in the presentation, and pretty much everything else is like kernel debugger screenshots, so do not worry. So if you have this opportunity, you mostly do not want to get detected. And to do so, you mostly don't want to look like, I don't know, malware.exe or any kind of weird process or executable. And it's often preferable for you to seem like you're some kind of legitimate process. Even more beneficial if you're able to do your malicious stuff from a process that does similar stuff. For example, if you're connecting to the internet and talking using SSL or whatever, you would like to use a browser or something like that. And there are numerous techniques that allow you to do something like that. The most prevalent category of those techniques is called process injection, which is actually made out of two main primitives. First is a write primitive, meaning that if I want to execute in the context of another process, I would like to have my code inside of that process. Now, there's a lot of different APIs, techniques, and whatever that you can use for that. You can manually allocate memory inside of that process and then write to it. You can map shared memory. You can do a lot of stuff. But in the end, there's the write primitive that allows you to have your code inside of another process. The other primitive that you need for that is an execution primitive, because, oh, cool, you have your own memory inside of a process, but like, who's going to execute it? Why would that process run your code? So there's a bunch of different APIs that your piece of malware could use to actually divert the execution for that process. Now, you could start a new thread in that process and make it start executing your code. Or you could try to divert, at least in Windows, the execution of an existing thread using things like setThreadContext or APCs. But this is not the only category of this kind of masquerading attack.
So another alternative is using something called process hollowing. Unlike process injection, when you take an arbitrary process and introduce new code to it, in process hollowing, basically you create your own process with a legitimate binary, and you somehow replace the code with a malicious one. How it basically works is you create a process in a suspended state, and before it actually starts running, you unmap all the legitimate memory of the process and replace it with your own one. Then after you remap the process, you're just taking the initial thread and redirect it back to the new starting entry point of the process. After you're completing the redirection, you just resume the initial thread and the process starts the execution, but it's running the malicious memory. So in the last few years, we observed a new stealthy execution technique, which the fundamentals of it is basically unlike process hollowing that uses a lot of memory operation. I mean, you go ahead, you remap the files, you unload some memory. There's a lot of memory operation in between. This specific class is focusing on the file system itself. And the target of this class is basically create a malicious process from the disk and somehow do not leave any records of it. The thing how it's works is by somehow allowing the attacker, before the process starts execution, to somehow revert the malicious content from the disk. So basically, the process is launched from a malicious image file, and then the image file is being somehow rolled back, and a benign content is being overwritten to the file itself. And when the process starts the execution itself, there's no actual content to actually scan. So there's a bunch of examples in the last few years we observed. One of them is called process doppelganger, for example, that uses NTFS transaction. Basically, they create a file with a transaction context. They overwrite a benign file with a malicious one, and they create a process from that file. But before they start the execution of the process, they just roll back the NTFS transaction, and they never commit it to the disk. So the real content really isn't really committed. Another approach another technique we've seen in the wild is called process hyperdeveloping. Basically, like process doppelganger, they get the same execution primitive. They somehow get a writable handle to the process file, and they just overwrite it with the benign content. And again, in the same way they do it before the process execution. And again, when it starts execution, we have nothing to scan for. And the last technique we can talk about is process ghosting, which basically leverages deletable handles to the file, and they actually delete the file before the process starts execution. So when we want to scan it, there's nothing on the disk. So let's talk about our motivation for this session. So we've seen all those kind of techniques, and we want to understand which OS properties make them work. Because if you think about it, it's a process, and it has a backing file which is completely different from its memory, which doesn't make a lot of sense, right? So we want to find out which dependencies and which primitive they are using inside the OS to actually understand how they work. And once we find all the common ground and all the primitives they are actually using, hopefully we can build a robust detection mechanism that allows to detect those anomalies and hopefully break the entire class and not just those techniques. So when does antivirus scan files? Optimally, we would have scanned a file each time would have changed, right? And for every change, we go ahead and scan it and see the actual content. The problem is that from performance perspective, it's not really acceptable. You can't scan file all the time. And so how we do it is basically try to scan it in a stable state. For example, when the file is being opened for use, we know it's not during editing or something, we can safely scan it now. Another option is during the cleanup procedure. A cleanup is where the handle for the file is being closed, and the user basically says, I'm done using the file. I'm done editing it, I'm done reading, and that's a really stable point for us to go ahead and scan the file. Another option is when a section object, when we will talk about it a bit later, is being created on top of the file as a part of the process creation, for example. Because it needs to be in a stable state to create a section, that's a good place for us to scan as well. And the last, probably more optimal place to scan is when the process is actually created. As an antivirus, we can see those kind of events, and that's a good place for us to go ahead and scan the file before we allow the process to execute.
Right. So to understand how this kind of technique can even exist, which is basically some kind of time of check, time of use attack, because the moment we are able to scan the process or the file, it's completely different from what we are expecting to be on disk. We need to understand what can happen before that last opportunity, before the process actually starts existing. And to understand that, we need to understand how the kernel views process creation, or how a kernel antivirus driver could view process creation. So process creation notifications or callbacks have been designed for this express purpose. It's to allow a driver to inspect every single created process and say, oh, this is good, this is bad, I want to do something to this. Now, counterintuitively, process creation notifications are not executed when the process object is created, but rather when the initial thread is inserted into that process. And this is invoked in the context of the creator process and not the one that is actually getting executed. Now, this small distinction might not sound interesting until you start diving into the internals of Windows process creation. The modern way to create processes in Windows is through a syscall called NtCreateUser Process. Now, this syscall gets an executable path as an input, meaning that, oh, here's the path to, I don't know, cal.exe and whatever. And when it enters the kernel, it opens the file on its own, creates the process object, inserts the first thread, does a bunch of other stuff, and then returns. This means that from the moment I actually call this function, and when it returns, I already have an operational process, perhaps not fully operational, but something that already has opened the file, already created the process object, already has code, and that code can run. And there's really no time of check, time of use thing here, because I can't really play around with the file as long as this syscall is executing. And the process creation callback, as we've said, is executed and invoked during initial thread creation. But this initial thread insertion into the process happens within the context of this syscall. So looks like we're OK. Here we have our process creation callback being executed in this call stack. And we can see that NtCreateUser Process is somewhere near the base of the kernel mode call stack. So we should be OK. No time check, time of use, no race conditions. The problem is, this is not the only way to create processes in Windows. And actually, before Windows Vista, there was another pair of syscalls, NtCreateProcess and NtCreateProcess.ex. Now, this syscall pretty much breaks every single assumption an antivirus or an endpoint protection solution has regarding process creation in the kernel. First of all, you don't really get a path to an executable as input, and instead you have a section object that you need to obtain from previously opening a file on your own, creating a section from that file, and only then submitting it as an argument to that syscall. This means that between the creation of the file and the execution of the syscall, we have arbitrary time that we can use to do whatever. The second thing that's interesting about this syscall is that it creates exactly 0 threads in the process. Why is that interesting? Because, as we've said, the process creation callbacks are executed within initial thread creation. So we can open the file, do whatever, create the process, do whatever, and then create the initial thread. And we have this huge opportunity of arbitrary time in which we can do weird stuff to the file. Now let's look at a generalization of all of our attacks of process ghosting, herpaderping, and doppelganging, and also a couple of other unpublished variants. So the attacker opens a file in some kind of modifiable state. This could be using a write handle, this could be using a share write handle, delete access, or even just a volatile transaction that could be rolled back. After this, we introduce malicious content to that file, and we don't close the handle. And as we've said, we can't just scan on every write. So this is just one more write. Nothing happened to this file that puts it into a new stable state, so no scanning. We then create a section and use that section to create a process. Again, it's still not time for a scan, because if you scan at this point for every process, you will not be able to, run any actual application code between your antivirus scans, and will make your customers extremely angry. So we still cannot scan at this point. We then can revert the changes, delete the file, roll back the transaction, override the file with whatever, and the section bits in memory are unchanged, because that is already something that has been mapped. And only then can we create the initial thread of the process. And now we have a process with malicious content and some weird file, or maybe even a non-existent file, but something that an AV really cannot find on disk and didn't have any opportunity to scan before we did our evil stuff. So what do we want to detect here? We want to detect 2 things. One is this legacy process creation API usage. Because if you use the modern process creation API, you don't have the opportunity for a time of check, time of use. So if we don't have the opportunity to abuse this, the process creation is not interesting. The second thing that we want to understand is whether this time of check, time of use was abused, meaning that someone has actually done something weird to that file from which the process was created. Because it's not enough to have just legacy APIs, you actually want to find an attack. And when do we want to see this? We want to see this as late as process creation notifications, because we want to be able to stop this malicious process or this potentially malicious process from executing. And we want to do this using minimal scanning, because again, if we always scan, we can't run application code. And while this is more secure, throwing your computer out of the window is also more secure. And we really want to run some kind of code. So first, let's talk about legacy process creation. So there are common patterns for this kind of detection work, which really aren't applicable because we want to detect this from the most privileged place we can, so that user mode attackers can't really bypass our stuff. First of all, you could use user mode hooks, but you're basically trying to mess around with a process that's completely controlled by an attacker, and they can always unhook your hooks. It might take a bit of effort, but there's no vulnerability involved. They will always do this if they need this. Another thing that you can do is call stack analysis. The user mode call stack can also be forged. If I wanted to look that there was some kind of arbitrary call stack, I can just push the same addresses to the stack itself and then jump to whatever code I wanted to execute from. So I can push all of my arguments, or I actually can push a bunch of addresses, push all of my arguments, jump to whatever syscall stub I want, and then I have an arbitrary user mode call stack. Kernel mode call stacks are also problematic because there's a lot of ways to create processes and threads from the kernel, and operating systems change constantly. So we can't really rely on one call stack remaining the same. So this is also quite unreliable. We could try to look at the bits in memory versus the bits on disk at some point, but this is again a strong perf concern, so we do not want to do that. We want to see if there's any way to detect this with zero scanning and with zero reliance on user mode. So to do this, we've discovered we can use something called NTFS file extra create parameters. This is a Windows file system feature that allows the kernel and other file system drivers or mini filter drivers to supply some kind of context to the file creation operation of the file. Why do we want this? Because, for example, it's useful for a file system to know whether a file was opened remotely or whether a file was opened by some kind of weird kernel feature or file system feature such as the prefetcher, so that the operating system itself can treat it somehow differently. Now, extra create parameters are basically just some kind of key value store where the key is a GUID that tells you which kind of extra create parameter this is, and the value is some kind of struct that, well, whoever needs to read that extra create parameter knows how to use. Now, something funny about extra create parameters is that there's a couple of documented kernel mode Windows APIs that check whether this ECP, extra create parameter, originated from user mode or from kernel mode. And this actually checks a bunch of internal kernel structures in the RP and the request packet for the open request, and checks whether there's a special flag there. And this sounds interesting, but there's actually no user mode functionality that can supply that. So this entire function is a no-op, and it's a no-op. And if you're in user mode, you can't really forge any kind of extra create parameter. Now, why is this interesting? Because during modern process creation, NtCreateUser Process actually opens the file that we supply as a path and appends a specific extra create parameter to it. It was actually made for AVs, but not for the express purpose of our attack. And this thing actually contains the token of the creator process, but that's not as interesting for us. What's interesting for us is that we need to supply to the legacy API an open file handle, or even a section created from an open file handle. And if we're opening this from user mode, there's no way we can make this look as if it has this ECP. So right now, we have an unforgeable way by user mode to differentiate between modern process creation and legacy process creation. Meaning that now, if we don't see this ECP in the open request for the file, we know that, oh, there's a chance time of check, time of use attack could be abused. But as I've said, this is not enough, and we need to understand whether this attack was abused.
So as we understand that basically legacy process allows the attacker the gap of the window that it can modify the file before it actually inserted the initial thread and gets scanned. We still not understand why there's a process and a backing file which are completely not the same, which is not make a lot of sense. So let's dive in a bit to the Windows Memory Manager. The first object we're going to talk about is section object. A section object is basically an object that represents a shared memory across the operating system. There are basically two types of section objects. One of them are file-backed, basically shared memory that is created on top of a file. It can be a data file, just like any text file or Word document, which is basically the same as you see on the disk. And there's also can be an image file that you can back up, like in Process, for example. The other type of section are page file section. Page file section are basically a shared memory that is not backing by any file at all. Basically, it's also called like memory section. Basically, you can share a bunch of memory pages between different processes, and it works just fine. So when we talk about section mapping, how we're going to map this section into memory, there are two types of section mapping. One of them is data mapping. Basically, you want to write to your Word document and you want to map it. The data that's in the memory, it's the same as in the file. It's basically a reflection. Every byte offset in the memory is the same as in the file. But unlike data file, mapping an image file is a bit more complicated because it's highly rely on the PE format. If you recall, PE format contains a lot of sections. There's the text section with basically the code, which is readable and executable. There's the data section, which is the read and write. And all those kind of sections should be reflected differently in memory, because in the process memory, it's not like one bulk of memory, read, write, execute. Every section defines the layout of the memory. So there's a more complexity for mapping image files. The other structure we're going to talk about is the control area. So when each time process wants to open a shared memory to map it so it can use it, it goes ahead and creates the section object. Each process has its own section object reference, but we need somehow to connect all of them together so all the sections will point out to the same pages, so we can actually share data. So each time a section is initially created, there's a control area that is created by the memory manager as well. And the control area basically holds and maintains all the metadata we require to go ahead and actually manage those shared sections. Either it's the segments, it's the permission for the file, how many views are all currently mapped on the control area. Everything that the memory manager needs to know is centralized in the control area. Now, it's important to note that because, as we've said, there are different types of mapping data in images, there's a control area created for each type of mapping. There's a single control area for all the data mapping pointing out to one file, and there's also an image control area that's pointing out to the image mapping. And the last or prototype PTs. Segments basically itself. Basically, it holds an array for this section, and it's just an array of PTEs. But it's not a normal PTEs, it's our prototyped PTEs. Prototype PTEs are a special kind of PTEs They are not really used by the hardware, by the MU to go ahead and just execute code. They are specifically used by the memory manager to cache the physical pages for the shell memory. Now, each time a process wants to go ahead and map, if the memory manager goes ahead and fetches proto PTEs. So if PTEs, that's going to be now let's talk a bit about section and backup file miscoherency. So we know that the fact is that those techniques cause a process to run malicious code, while the backend file is completely different. And for obvious reasons, there's some sort of miscoherency between the memory and the backing file. But if you recall, creating a section image requires a handle to a file. Section image cannot be created on the page file handle. So you cannot really create section images that are totally on memory and not upon file. But when this section is created, it's a responsibility of the memory manager to guarantee that the memory and the backing file will be coherent for all the life of the section, because eventually when there's paging IO from, we need to move the pages back to the file, and then we need to read from the file back when we want to restore execution. So it's the memory manager guarantee to provide it. But as you've seen in all those techniques, the attackers somehow used a modified handle, like using transaction object, writable file handle. They don't use a read-only handles. And if you think image section, but it knows that the underlying, it can't guarantee that it will file, and then the next paging IO, the process will. So in that point of the section creation, doing those guarantees. So what it's actually to be backed up by the page file instead of the file. It goes ahead to the physical pages, make sure they go back to the page file and not the file itself. So it basically decouples between the two, because it knows it can guarantee the coherency, and the result is that you have an image section which is backed up by the file. There's a file path and all seems good. So what we that we have a suspicion that rather by some arbitrary memory pages that have nothing to do with the file. So as the memory manager goes ahead and inspect the file object and check if it's deletable any what we call writable references, it automatically decides let's move it back to the page file, and it does it in the section creation. We can do the same thing and look in the process file object, which is the same file object in the section, and see if it was open with writable access, deletable access, anything thought of that, and understand that if this how the file memory manager decided that it can guarantee the coherency and everything should be moved back to the paging file. So we can mark the process highly suspicious, as we know there's most of the chances it's really running on memory only.
Right, so now we have two primitives for detection. The first is how we detect this legacy API usage. And as we've said, if there's no NtCreateUser Process ECP, this means we are using, almost in every case, except for a couple of very scopable edge cases, we are actually using the legacy API. And if you're somehow able to forge this thing, because this is not a user mode functionality at all, this probably means you have some kind of kernel read-write primitive, which, well, you can do other better stuff with a read-write primitive in the kernel. So we can safely assume that if you don't see this ECP in the file creation operation, then we are talking about this legacy process creation API. And this gives us opportunity for time of check, time of use. And just as Amir has explained right now, we know that a file has probably been abused because weird stuff happened to the file backing the actual image section of the process. Because if this section coherency thing is broken and you can make something that doesn't make the memory manager mark all of those pages as dirty, you have a much more significant problem, because now this is an OS stability problem. Because if my code gets paged out and then Windows tries to take this code from an entirely different file, I can override the kernel. I can override, I don't know, some kind of driver. I can override pretty much every piece of code that should be protected. And this is a much more significant security and stability problem. So as long as we assume there's no super cool 0-day happening here, we can assume that, again, no kind of user mode thing can forge this information. And those two things together, as we've seen from our data, as we've seen from analyzing the code of the OS, are pretty much a surefire detection for every single one of the techniques we've mentioned, and for any potential variation on this schema, because as we've said, if you can't forge this information from from the user mode, and if you have any other way that you can basically pull out the memory rug from under the process and do something weird to the file, the memory manager will know, because it has to know, so you don't get a blue screen. So together with that, we now have this super stable 100% true positive detection that really can't be bypassed by user mode. And as I said, we've tested this against a couple of other unpublished variants. And while there is a way to bypass this, this is actually, using some kind of driver. And again, you have a kernel read-write primitive, so do other cooler stuff if you're using a malicious driver. So we at least believe this entire class of techniques could be caught by our stuff. And if you want to do something else, you have to actually innovate it, do something novel, and not another variations of, I don't know, process bamboozling or whatever. And that's it. Thank you for listening. We have a ton of time for questions. So there's a couple. Yes, of course. So we were asked about false positives and examples for false positives. So one such example is process cloning, which is the weird name we Microsoft people call fork. Now, when this happens, a lot of weird stuff happens. There's a bunch of APIs that clone a process and then don't use the ECP. Even though it's the modern API, there are other APIs that create a new process using NtCreateProcess EX, but then this process can never run code, so it's not interesting for our case, because go ahead, open a new process that can't run code. I mean, I won't stop you. But yeah, so those are the two main ones. That's all operating system functionality. You have IDA, I suppose. Anyone else? Well, it's time for us to take a drink then.